Okay, hello everyone. Welcome to our webinar on Introduction to the latest COMSOL Multiphysics features. My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at COMSOL and the major updates to it. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. This webinar meant to be people already familiar with COMSOL Multiphysics, but feel free to contact us at any time during this webinar or after by email. COMSOL is a multiphysics modeling, simulation and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you have completed your COMSOL simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software like MATLAB. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And the major news in 5.3a. Some of the news include copy-paste and insert of components and physics interfaces, save plots. You can save plots in the model for faster rendering when you open a model with plots that take time to render. We have extended the boundary element functionality that was previously available for corrosion and electrostatics into magnetostatics and acoustics. There's a new revolutionary method for so-called capacitively-coupled plasmas. Plasma is important for semiconductor manufacturing, and later you will see why we call it a revolutionary method. Buoyancy-driven turbulence in the CFD and also heat transfer module, and the big update for the structural module is the shape memory alloys. Now it's available to define these kind of physics. There are many updates to the global definitions and to the COMSOL server as well. For the studies and modeling, since a few years now we have had an algebraic multigrid solver type of iterative linear solver that can be used for a number of applications. The most important one is CFD. Since the last 5.3 release, we have seen up to 40% performance improvements. The geometric multigrid method, or GMG method, has up to 20% performance improvements. When you use a nonlinear solver in COMSOL, you get the option of using a direct linear solver or an iterative solver. When you use the direct linear solver, you will now see up to 30% improvement thanks to the fact that we are reusing the reordering between each iteration. Moving mesh has moved under definitions, under components in the model tree. It was previously available as a separate physics interface, and now it has been elevated to a more central location. This makes it easier to set up multiphysics problems that use a moving mesh, for example, rotating domains. We now got a new framework for model reduction. We are planning to use this in the future for a variety of purposes. So this is the first step in implementing model reduction using a number of different numerical methods. In this release, we got two methods, model analysis and asymptotic waveform evaluation. To the right here, you see two different cases of model reduction for an acoustics model. This is a frequency sweep for the transmission loss of an automotive muffler. The blue curve is the original. It is the same in both figures. Then we got these two green curves. The top figure shows the frequency sweep using the 6 lowest eigenmodes, and the lower figure shows the same type of sweep, but now with 20 eigenmodes. You see the agreement is better the more eigenmodes one takes into account. Since we include the lowest eigenmodes, we get very good agreement at the lower frequencies and worse for higher. But again, better the more eigenmodes we include. More eigenmodes, of course, means more eigenvalues. If you have the live link for MATLAB, you are going to get access to reduced models through a new state space export function. Some news in the model builder. The Model 3 has been upgraded and have a slightly different look that is more Windows standards. One can say if you forgot to add the selection like a boundary for a boundary condition, you now get a warning indicator in the Model 3 on top of the feature node. You can see it in the screenshot to the right where the tooltip says selection is empty. I briefly mentioned copy-paste and insert of components and physics interfaces in the beginning. I just wanted to point out that this functionality is available within a COMSOL session and also between two different COMSOL sessions. You can now have user-defined functions in parameters. For example, you may have defined an interpolation function, and now you can parameterize your geometry based on such an interpolation function, like the position of a cylinder. In the picture below, you can see such an example. In the next slide, here you can see it in a bigger picture. So you can see there is only one. Here under the geometry node, there is only one cylinder subnode and one copy subnode. And here, the elevation, the z displacement is defined by a parameter included in an interpolation function. Some few words about material libraries. In the material library add-on product, you will have 150 new materials and 1300 new material properties. This includes new types of thermoplastics, hot work tool steel, plastic mold steel, and others. With the RF module, we are now including more than 60 substrate materials from Rogers Corporation, a well-known company in the microwave circuit materials industry. Some news on graphics and results. We are going to have support for space mouse devices. This is a type of 3D navigation mouse used extensively for navigating CAD models in dedicated CAD software, and we have gotten numerous requests for it over the years. Now it's supported in 5.3a. You can now choose to save all the plots in the model so that when you load the model again, you don't have to wait for them to be regenerated. This is important for particle tracing, for boundary element models and larger models in general. And the rotation of center, it's a highly requested feature. Now it's easier to rotate around in the graphics window. And there are the two new buttons, first and last buttons, when you have parametric solutions. And a new color table, it's called CVDIS. And a new animation format, it's a WebM. It's a more modern, more sophisticated algorithm, so you can use this if you want to export your simulation results. CFD and Heat Transfer news. There is a new realizable K-epsilon turbulence model, so now you have much more sophisticated models in the turbulence models section. In both the CFD and the heat transfer module, buoyancy-driven turbulence is now available, and all turbulence models are now available for multi-phase flow, and rotating machinery is available for all flow interfaces. That's a huge and big request that we got over the past years. On the heat transfer side, there is a new type of inlet with more realistic temperature distributions. It lets you define the upstream temperature and pressure instead of bluntly setting the temperature uniformly across the inlet. It computes the enthalpy and uses this information to set an appropriate heat flux at the inlet. A new moisture flow multiphysics coupling and a new Beer-Lambert interface for absorption of light, typically laser light in weakly absorbing media. This is available as a new physics interface called radiative beam in absorbing media. Big update for the chemical engineering module. In this module there is a new built-in library for thermodynamics properties. You use this together with the chemistry interface for just about any mass transport and chemical reaction model. This is a quite substantial improvement to the chemical reaction engineering module, and we will cover this in a dedicated chemical engineering webinar later on. Electromagnetics. The AC/DC module has a new interface for magnetostatics based on the boundary element method. This is a great complement to the finite element method, and it allows you to evaluate the magnetic field anywhere, not only in the near field but also in the medium and far field with great accuracy. For example, it can be used in analysis for placing magnetic sensors. It is convenient, you can use it together with a finite element formulation instead of infinite elements and retain the capability to evaluate the field outside the finite element modeling domain. The AC/DC module also has a new soft magnet material model that can be used to analyze demagnetization effects, for example in permanent magnet motors that are now becoming popular for use in electric vehicles. In the RF module there is a new study type called adaptive frequency sweep. This automatically uses the asymptotic waveform evaluation solver, which is a reduced model technique that is particularly useful for frequency sweeps. And as I mentioned earlier, the plasma module has a huge and a big update. We call it revolutionary. It's a new method for capacitively-coupled plasmas, or CCPs. This is based on a nonlinear time periodic formulation. Many of our plasma module users have been asking about this over the years, so this is some great news for this community. These types of CCP model haven't really been possible to analyze in previous versions. If you managed to set them up, you were looking at solution times of weeks. Now we are looking at solution times of hours. We are not aware of any competing software that is able to perform such simulations this efficiently. Updates to the acoustics module. In the acoustics module, there is a boundary element method, so it's extended to the acoustics field, but it's more than that, just a simple boundary element method. You can connect boundary element domains with structurally vibrating domains such as shells. This is what you see in the picture to the right here, a combined finite element and boundary element model where you have a structural shell connected to finite element acoustics domain inside the speaker and the boundary element domain outside the speaker. You can analyze the sound pressure level at any point in the model. In the picture below here you can see the sound level at about 10 meters away from a speaker. With the finite element method you would have needed something like 0.5 billion elements to get the same results. Some other acoustics news: impulse response for ray acoustics. Again, lots of users have been asking for it over the years, and everything is included in the acoustics module. Another new model in the application library, acoustic scattering with boundary element methods. You can find this example inside the application library. Here you can see the reflection from an obstacle, that's a sphere, very far distant from our transducer, and between the obstacle, between the sphere and the transducer, there is no mesh. So boundary element method has a very big impact on these kind of simulations. So now I jump into COMSOL to open up the loudspeaker model to see how it looks like and what kind of interfaces are there. So here we have several multiphysics nodes within the component, and in the component, as you see, this is our geometry. We use the symmetry conditions, so we model only the half of the geometry, as you can see here. We have pressure acoustics, where we have air inside our finite element domain. We have a shell where we have thin elements like the speaker itself, the membranes. We have solid mechanics where we have the cabinet of the speaker and the stand of the speaker, and pressure acoustics boundary elements for modeling the wall and the floor in the simulation, in the environment, as you can see here. So we use symmetry conditions. We set up one layer for the floor and another layer for a wall at the back of the loudspeaker. And these can be set up here in the infinite boundary condition. So you can just put the positions of those planes and you can set up different conditions for that one. And to couple the four physics, you have several multiphysics nodes. So you couple the acoustics to the structure, you couple the shell to the solid, and the acoustic boundary to the fan boundary, and an acoustics to the structure boundary, to the shells, to the membranes itself. And with this boundary element method, you can evaluate any field anywhere, not just inside the finite element model, but outside in the boundary element model itself. This is the acoustic pressure, and what we want to look into that you have seen in the thumbnail image. These the sound pressure levels at different locations. So you can see the original geometry and some duplications, and in the boundary element method color you can see the sound pressure level, and that's another representation. So with this new feature, with this new boundary element method, you can include much bigger models with much lower stress and computational effort that you could do with the finite element model. Back to our original list, structural mechanics news. You've got a solid beam connection directly in a 3D, and also you have the bore thread force modeling with contact pairs. It's much more precise and sophisticated than the previous version. And now there is a third option, a generalized plane strain option in the solid mechanics interface that's also available. And in the nonlinear structural materials module, the most updated and the most biggest feature is the availability of shape memory alloys. From the geomechanics, there is a new elastoplastic material model, and for the multi-body dynamics module, there is a new boundary condition that's called the cam follower condition. So if you go back to COMSOL and we open up the cam follower, we can see how does it look like during the simulation. The model is already solved, so I prepared it for you, and this is the result that you can see here. So we can see and we can create a very nice animation from this one. So this is a new type of boundary condition, so now you can include this on top of the structural mechanics module. This functionality is inside the multi-body dynamics module. So these are the major and the most important updates, but there are much more sophisticated and detailed updates. So we will cover all of those updates in a separated webinars later during this month, both for CFD, for structural mechanics, and other modules that are interested. And with this, it wraps up my presentation. So I go to our last slide where you can see some contact information and what kind of materials are available there. So just to close up this session, I will share this last screen with you. So if you need some other questions, what kind of physics can be solved with COMSOL, what kind of properties can be added, feel free to contact us. You can see our website, and you can write us directly. If you want to try out any of the new features or any features that can be used in COMSOL, just feel free to contact us to get a free trial version. And you can search for previously recorded webinars and videos and events on our website, and you can download all of the materials and all of the models at our website at comsol.com also. And we will include this recorded webinar in the follow-up email, so if it was a bit fast for some of you, don't be shame, so you can recap everything from the recorded webinar. So this wraps up my webinar. Thank you for watching us, and see you in the next webinar that covers the new features in the CFD module. See you in this month later. Thank you for watching us, and bye.